time slots be marked by light, solid gray lines. Okay, right? To produce a 1-bit, halfway through the time slot, we increase voltage, or we make a positive voltage. To produce a 1-bit, we hold that positive voltage until halfway through the next time slot, we go to negative voltage. Okay, to produce 1-bit, halfway through the particular time slot, we produce a positive voltage. Okay, and so forth. Note that during this pattern, the bit indicator happens midway through the time slot, opposed to at the beginning of the time slot, as in the case of the traditional non-return to zero. This is a non-return to zero type pattern. However, again, the bit indicator happens midway through the time slot. All right, continuing with the 10 base T standard. Okay. Again, it requires a minimum Cat3 cable. A Cat3 cable, Cat5 cable have 4 pairs of wires. However, in regards to the 10 base T standard, 2 pairs are used. Right. In regards to the 100 base T4 standard, it operates at 12.5 megahertz. It uses a different type of encoding scheme from 10 base T, and it has a data encoding scheme as well. Okay. It uses 4 pairs and requires at a minimum Cat3 cabling. Okay. The 100 base T4 standard is not currently in use. The flavor of 100 base currently used today is the TX. It operates at 31.25 megahertz. It uses the MLT-3 symbol encoding, in addition to a data encoding scheme known as 4B5B. Okay, uses 2 pairs and requires Cat5 cabling. Let's take a look at the MLT-3 symbol encoding. Okay, you've had a few seconds to study the MLT-3 scheme. We see that it's a little more complex than the previous schemes. In this instance, to produce 1 bit at this particular time frame, there's a positive voltage. And notice what happens when the positive voltage in this instance is maintained. The next time frame will automatically be interpreted as a 0. So if we want to produce 1 bit after producing a 0 in the 3rd time frame, then we have to go to a different voltage level. In this instance, 0. And if we maintain the 0, the following bit will be interpreted as 0. Again, we maintain the 0 voltage, and the next bit will be interpreted as 0. To produce a 1, we have to change the voltage. In doing so, we produce the 1. If we want to produce a consecutive one, we have to change the voltage. And if we want to produce a third one, we have to change the voltage. But maintaining the voltage will be interpreted as a 0, as seen in this scheme. All right, under data encoding, we see that 100 base TX has a unique way of shuffling the intended bits before sending the bits across the media. And this unique code is known as 4B, 5B. Let's take a look at it. Okay. So if the sender needs to produce 0 hexadecimal character, the sender generally would just send 4 zeros, which is the equivalent of 0 in hex. However, if the sender is using 100 base T, then 4 ones and a 0 will be sent. The receiver, on the other hand, will also be, in this instance, communicating via 100 base T. So the receiver would be aware that there's a unique coding pattern, and the receiver will have to interpret the 11110 as 4 zeros and relay the 4 zeros to the upper layers of the OSI model. Okay. To produce a hex character, generally without using a unique scheme, we would generate a 1010 bit pattern. However, if we're going to relay the 8 hex character to another device via 100 base T, then our device will interpret the 1010 as 10110, and the receiving device will receive this bit pattern and then interpret it as originally being 1010. Okay. Your text talks briefly as to why 100 base T employs the 4B, 5B encoding scheme. Okay, so 4B, we want to send 4 bits, but in essence, we'll send 5 bits. Okay. Okay. We can also send signals across Ethernet using 1,000 bits per seconds, or 1 gig. Actually, it's 1,000 megabits per second, and the frequency employed is 31.25 megahertz. It uses a 4D